Hi folks, welcome back. This is 6.2. This is the second section in sampling distributions. We're going to look at sampling distributions for proportions. We're going to look over the formulas that go with that and the applications of it with normal curves and things like that. All right, so at this point in the year, we usually do another experiment in class. And the experiment we do is we roll Hershey Kisses and we see how many of them land on their actual bottoms. Like these three here, this is what we want landing on their bottoms, and with their little flags up at the top. All right, but what happens when you roll them is most of them land like this, they're on their side. Like this one's good, it's on its bottom, but like this one's on its side, this one's on its side, 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 right, on its side, on its side. Like most of these, a good portion of them are on their side. So what we want to do is we find the proportion that are standing up straight, and we take each one of those samples and we plot what our answer was for each one of those samples. So with this one here, this is our n was size 5. So we rolled 5. I think it's weird to say we rolled 5 kisses instead of rolling 5 die. But we rolled 5 Hershey Kisses, and this was 0 out of 5. These two rows were 1 out of 5. These two rows were 2 out of 5. These were 3 out of 5, 4 out of 5, and all 5 out of 5, not 6 out of 5. All right, so it was possible to get all of them up. It was also possible, and there was 2 different classes. That's why there's 2. So the first row here was one class, and the second row here was the second class. So there's really 2 distributions happening here. But both of them, you can see they kind of go up here, and then they kind of come down, and then they're real low over here. So it looks like they have a middle somewhere around here. Then we did the same thing, but instead of doing it with 5, we did it with 20. So we rolled 20 like this here, and we counted what proportion ended up standing on their bottoms. And this is the distribution we got. And if you look at this distribution, there's a big peak there, but it's getting closer and closer to being a normal distribution. And I would say the middle is probably somewhere just a little bit to the right of this big peak here. All right, so what happens is this becomes our sampling distribution. All right, we get all possible samples, or we get close to it. We get a lot of samples. And if we look at them, they have some sort of middle proportion. And in fact, that middle proportion, its center, it is the same as the population proportion, which is about a third of the time they land on their actual bottoms. All right, it becomes closer and closer to being symmetric. It approaches a normal distribution, and we have formulas and things like that where we can calculate its standard deviation. So let's take a look at that sort of stuff here. All right, so what happens with our shape, our center, and our spread? In other words, we just described these distributions. So what did we notice? Well, we noticed that as our sample size n increased, it became closer and closer to being a normal curve. All right, and this does depend on both n and whatever the population proportion is. And then these samples will approach, all of the sampling distribution for all these p hats will approach a normal distribution. We'll go over exactly what you need to be normal here in a minute. All right, the center of the sampling distribution, which is mu sub p hat, is equal to the center of the population. All right, those two seem to match each other. All right, this makes sense because this should be an unbiased estimator. All right, when we're rolling those Hershey Kisses, there's nothing biased about that. It's an unbiased estimator, each one of those p hats is, of the actual proportion p. So the spread should be getting smaller, and they should be getting closer and closer to the actual proportion. And speaking of spread, the standard deviation of the sampling distribution, this is what this symbol means, standard deviation of the sampling distribution, gets smaller as n gets larger. The bigger n gets, the smaller the standard deviation for the sampling distribution is going to be. And then it does depend on both n and p. So we'll have a formula for calculating it here in just a second. All right, and so remember, if we want to do p hat, it's the number of successes in the sample over the size of the sample. So it's x divided by n. We're going to use that here to come up with some formulas in just a second. All right, so think of this as binomial. So if we want the mean for a binomial distribution, it's n times p. Well, our p hats are x over n. So if we multiply, we can really think of this as 1 over n times x. And if we multiply this 1 over n times x, right, times our, well, if we pull out this 1 over n from it, we get x times p, or this n times p for our total sample. Basically, we get the formula that the mean of the sampling distribution is just equal to p for any unbiased estimators, which is all of what we're going to use in this class, unbiased estimators. All right, if we do the same calculations here with this, we get what's called our sampling distribution. We're basically multiplying it by 1 over n. We're just taking each of these and we're multiplying it by 1 over n for our standard deviation, and we bring the n inside, and we write it inside as the square root of n squared, and then these n's are going to cancel out here, and we're just left with this as our formula. All right, so you can see, since we have the n on the bottom, as sample size increases, the spread will decrease. So as n gets bigger, the standard deviation of the sampling distribution will decrease. That is important. They love to ask about that on the AP exam. And it's because we're dividing by n, well, the square root of n. But since we're dividing by a bigger number, our answer gets to be a smaller number. All right, so here it is again, all of it together on one page. So if we're choosing a simple random sample or any random sample of size n from a population of size capital N with proportion p, so the population proportion is known or was known for some previous population, p hat is the sample proportion of successes, then the mean of the sampling distribution of p hat is p. The standard deviation of the sampling distribution of p hat is the square root of p times 1 minus p over n. Notice this is p, not p hat. So we're not using the sample here, we're using the population. Later on, we'll actually use p hat if we don't have p, or we'll use 0.5. We'll kind of choose. All right, and this works as long as our sample is less than 10% of n. Remember, this is our independence. We need to make sure our samples are independent of each other when you're taking these random samples, and as long as they're less than 10% of the population, or 1/10 of n, less than or equal to 10% of the population. We're going to use this condition later on in class a lot. All right, as n increases, the sampling distribution becomes approximately normal. Notice we have the word approximately here, but yes, it is really close to normal. So we usually just say approximately normal. We don't just say it becomes normal. All right, but before we can pretend it's normal, we have to check these two conditions. So condition 1, n times p has to be greater than or equal to 10. And condition 2, n times 1 minus p has to be greater than or equal to 10. In other words, we have to make sure it's not too close to one of the axes that the tail of the normal distribution is getting cut off. Like if it's too close, it's going to get cut off and it's not going to be a normal distribution. If it's far enough away, hey, it'll fit the whole normal distribution. So that's what we're checking by checking these two conditions. All right, so example problems. So a polling organization asks a simple random sample of 1,500, that's a big sample, first-year college students whether they applied for admission to any other college. In fact, 65% of all first-year college students applied to colleges besides the one they are attending. That sounds like population information. What is the probability that the random sample of 1,500 students will give a result within 2 percentage points of the true value? Well, this is a lot of information here. Let's see. What should we do first? Well, let's start by stating what we know. So we know our sample size is 1,500. We know that the true p for the mean is 0.6, or for the population is 0.65, which is also the mean of the sampling distribution of all those proportions. And we want to be within plus or minus 2 percentage points. So that'd be 0.02, plus or minus 0.02 of the actual. All right, so we got to check our 10% condition. So we're going to use this p here, and we're going to use this n. So we got n times p is 1,500 times 0.65. And the other one is n times 1 minus p, which is 1,500 times 1 minus 0.65. And we want to know, are those bigger than 10? Like, I can look at that and say that's probably going to be much bigger than 10. But if we just pull out our calculator and plug it in, we got 1,500 times 0.65 equals 975. All right, this one is the complement, so it'd be 1,500 minus the 975, right? We could just distribute here, and that's what that gives us, but that's 525. Both of these are clearly greater than 10. We do want to write that, and we can put little check marks after it. So yes, this is approximately normal. All right, so now we can treat this as a normal distribution. So now we need to know what's the mean and standard deviation of our normal distribution. Well, the mean we've got. There's our mean right there. Standard deviation we need. We're working with a sampling distribution. So the formula is the square root of p times 1 minus p over n. So this will be the square root of 0.65 times 1 minus 0.65 over 1,500. All right, so we bring our calculator back out. We got the square root, second square root, 0.65 times 1 minus 0.65. I know a lot of you could probably do that in your head. I'm just going to write it out. Then divided by 1,500. Enter, should be pretty small. 0.123. I'm sorry, 0.0123. All right, 4 decimal places is plenty, probably more than you need. All right, next up, oops. So yes, we can use the normal approximation. Next up, find the probability using normal CDF. All right, so we know our mean. We know our standard deviation. What are our lower and upper bounds? If we're using normal CDF, we have to have bounds. Well, it said we want our results to be within 2 of the actual. So the lower bound would be the 0.65 minus 0.02, which is 0.63. And the upper bound is going to be 0.65 plus 0.02, which is going to be 0.67. The mean we're going to use is the 0.65. The standard deviation we're going to use is the 0.0123. So we go back to our calculator and we're just typing this in. Let's move it out of the way here so we can see. So second distribution, normal CDF is number 2. We're going from 0.63, 63%, to 0.67, 67%, because we want to be within 2% of the 65%. Our mean is the 65%. Our standard deviation is the sampling distribution standard deviation that we just calculated. And if we work that out, we get 0.896. All right, so that is the probability that one of these samples of 1,500 students will get somewhere between 63% and 67% that say they applied to multiple colleges. More colleges than just the one they went to. So it looks like almost 90% of people applied to multiple colleges, which I suggest you guys doing as well. Don't just apply to one school. Apply to both. Have a safety school and shoot high for one of them. All right, let's try one more here. So a polling company wants to check if the proportion of voters who support national parks is near 85%, as previously reports have found. So that's a P right there. P is 0.85, which would be the mean for our sampling distribution of P hats as well, we think. They take a random sample of 1,000, sample size 1,000 registered voters. What is the probability that the random sample will be, this time we're going to, within 3? So now within 3 means when we're going to do our normal CDF, which hopefully we'll be able to do, but we'll have to check something first. Our lower and upper bounds will be 0.85 minus 0.03, which would be 0.82, and then 0.85 plus 0.03, which would be 0.88. So between 82 and 88%. We know the mean already. It's going to be the 0.85. But wait, we should probably check some conditions. So I don't know if we checked this last time, but I don't think we did. The 10% condition. Yeah, I didn't check that. So n equals 1,500 is less than 10% of all college freshmen. I mean, that should make sense that our sample is always going to be less than the 10%. It's pretty much always true, but we should say it somewhere. All right, so our 10% condition, n equals 1,000, is less than 10% of all, what we're talking about here, just voters, huh? Sure, we have hundreds of millions of voters in this country. 1,000 is less than 10%. Our normal conditions, so we need to know if we can use normal CDF or not. So we do n times p, which is 1,000 times 0.85, which is going to be 850. That's definitely greater than 10. We do need to state this part. N times 1 minus p is 1,000 times 1 minus 0.85, which is 0.15. We get 150, also greater than 10. That checks out. So this tells us that it is approximately normal. If we're doing this on a free response question, we want to write this. All right, now that we know it's approximately normal, we're going to use our normal CDF. We still need our standard deviation for this sampling distribution. So it is the square root of 0.85 times 1 minus 0.85, which gives us 0.15 over the 1,000. I am going to need the calculator for that one. I don't know that one off the top of my head. So we've got square root, second square root, 0.85 times 1 minus 0.85 is 0.15 divided by 1,000. Enter. 0.0113, I guess we could say. So that's going to be a standard deviation that we're going to use here. So we throw that in. Oh, not too far. Too many windows open here. All right, so second distribution, normal CDF. We're going from 82%, 0.82, to 88%, 0.88. The mean was what they gave us, the 0.85, unless we know otherwise, we use their mean. And then 0.0113, it's 29 or whatever, but that'll work. And we get 0.992. I usually like to write 3 decimal places, but really 2 decimal places is funny. So what proportion of the random samples will be within 3, I left out some words there, will be within 3 points of the true value? 99%, or 0.992 of the random samples should be between 82 and 87. If we took 100 random samples, 99 of them should be between 82 and 88. Maybe one of them was like 89 or 90 or something, who knows? All right, so that is how sampling distributions work with proportions. The next video we'll do sampling distributions with mean. There is a homework assignment that goes with this one, so check on that, guys.